Hello, welcome to Electronics Education. I'm Vincent Chang. Finally, with several foundations we laid out in the previous two lecture video, then it's time for us to investigate the stability of the non-inverting operational amplifier. Stability of non-inverting operational amplifier, important skill explained. Stability issue for the non-inverting amplifier. Make sure you know how to calculate beta of the series shunt feedback. It's a 3-pole transfer function, a 100 decibels DC gain, and 3-pole located at the 100 kilohertz, 1 megahertz, and 10 megahertz, 3-pole amplifier transfer function. So I urge you to use the hand analysis, right, to draw the first one, the magnitude response, negative 20, 40, 60 decibel per decade of frequency. For negative 20, 100 to 80. For negative 40, 80 to 40. For negative 60 part, the 40 to negative 20 decibel. Here's the magnitude response. What about the phase response? So here's the phase response. 4 segment, 45, 90, 90, and 45. And the richest, negative 20, 270 degrees. And I also answer the question, how accurate is the Bode plot? How accurate is the Bode plot? We found out it's not bad. Here's the simulation result for the magnitude response. For the phase response, it's quite close between the hand analysis and the simulation outcome. All right? So now it's time for you to investigate. Let me ask you. Just look at the feedback amplifier on the left-hand side. And combining with the frequency response, including the magnitude part and the phase part. So let me ask you, is the feedback amplifier stable or unstable? You get my question? I'm looking at you. Let me ask you, is the feedback amplifier stable or unstable? Can you make the judgment? Can you make the judgment? Yes or no? Yes or no? How many of you think yes? How can you make the judgment without knowing beta? Who has the final authority to determine the stability of the circuit? Loop gain. So the data is not sufficient, all right? Don't get confused between open loop gain A and the loop gain A beta. So data was not sufficient to make the judgment about the stability. So I haven't told you the beta yet. All right? So only look at the open loop gain. The stability cannot be decided. All right? All right? So you need beta. I'm laughing. But I hope you remember who has the final authority to make the judgment about the stability of the circuit. Loop gain. All right? So beta is not given. So we need beta. We need beta. But before I give you the beta, I want to teach you a conversion from open loop gain A to loop gain A beta. So I'm going to teach you a conversion from A to L, from open loop gain A to loop gain L. From blue to orange, from A to L. The conversion from A to L is blocked. Okay, I have to take out my video. So so focus on, you have the magnitude part, right? And you have the phase part. So the conversion involves two parts. So we need a magnitude conversion. We also need a conversion for the phase. So let's start with the phase conversion. The phase conversion from the conversion, are you with me? In other words, if I give you the phase of A, can you know the phase of A beta? Yes, you can. Why? Because what is the phase of loop gain? It's a signal starting from the red, going through the brown, and arrive the green. So how much phase he collected, got involved, introduced? It's the phase of the complex loop gain, right? This is the phase of the loop gain. But the purple network is the resistive feedback. So there will be no phase involved from brown to green going through the feedback network. Therefore, the phase of the loop gain is actually the point starting from red and the arriving brown. It's the phase of A. Because why? There's no phase involved, introduced in the feedback network. So we don't need a conversion for the phase. They are equivalent to each other for resistive feedback. If it's resistive feedback, they are equivalent to each other. All right? Get it? But we do need a conversion for magnitude. We do need a conversion for magnitude. You need a middle school math. I'm sure elementary school will teach you this. We need a middle school math. All right? Log AB equals log A plus log B, right? Or minus log 1 over B. So we need this because the conversion is going to be in the log scale. The conversion from A to A beta. The conversion from the magnitude of A to magnitude of A beta. So what's the difference? The difference relies on the 20 log 1 over beta. 20 log 1 over beta. From A, focus on the conversion from A, focus to A beta. Now beta is given 0.01. So if beta is 0.01, what about the term? What about the 100? What is the 20 log 1 over beta? 40, right? 40. Conversion from A to A beta. I want to make sure you understand it because this is super important. You are going to apply this for when you face the stability in the future. Even the bipolar or CMOS operational amplifier when you face the stability issue. All right. So 40 decibel. Let me take out this. So A, the blue one, minus 40 decibel. A, the blue one, the blue curve, minus 40 decibel. Which means what? Which means going minus, right? A minus cut 40 decibel, down 40 decibel, right? But there's another way to do this. You can fix the blue curve, but bring, let me go back, rewind. There are two ways to do this. Number one, let's fix the frequency axis, but bring down the curve. Or you can fix the curve and bring what? Bring up the frequency axis, right? So bring up by 40 decibel. So this is the new frequency axis, the purple line, for what? For what? For loop gain, for A beta. And the intersection represent what? Remember, unity gain frequency for loop gain, FTL. And at this frequency, apply what you learned before. Find out the corresponding phase. Find out the corresponding phase. Compare the corresponding phase with what degree? 180, right? Now it's beyond 180. Unstable. Unstable. Phase margin is negative. Negative 45 degree. Unstable. Another case. What about 0.0001, 10 to the negative 4 power? And the term, 80 decibel. So the new horizontal line, the new frequency axis, going up to 80 degrees, just look at the intersecting point, tells you the frequency FTL. Again, it's the unity gain frequency for loop gain. And at this frequency, the corresponding phase is 135. So stable with 45 degree phase margin. All right? So for the 0.01 is unstable. 0.0001 is stable. So somewhere in between is the boundary. It's the critical point. So what is the critical beta? What is the critical beta? Between stable and unstable, here's the answer. 10 to the negative third power. Why? Because at this frequency, the intersecting point, the corresponding phase is 180 degree. All right? Interesting, right? Zero margin. The zero margin. So what is the takeaway? Tell me. You tell me. What is the takeaway? Why this matters? When can I apply this technique? The title of this video, it says, an important skill explained. An important skill to investigate the stability of feedback, right? What skill? Why this matters? Because in many cases in the future, in an analog integrated circuit, the frequency dependent part comes from the open loop transfer function, right? So when an open loop transfer function, for example, an operational amplifier is given, but you have several different resistive feedback network, and you want to evaluate which one fits. You want to evaluate the stability for one operational amplifier, but different resistive feedback network, different beta. then you can apply this. You can apply this. You just turn based on this. Middle school math. Based on this, it relies on the conversion from A to A beta. I think you got it, right? You got it. So the conversion is to a 20 log 1 over beta. So you just check, you just put the beta into 20 log 1 over beta. This one. And you just draw a horizontal line. In the cases I just mentioned, there are 3 betas. So corresponding to 40, 60, and 80 decibel horizontal line. And just check, just look at the intersecting point, which tells you the FTL, the unit gain frequency for loop gain. And find out compare the corresponding phase with what? With 180 degree. Compare the corresponding phase with 180 degree. It will tell you stable or not. All right? So this is the takeaway. Very important skill that you're going to apply many times in the future when you face this similar kind of the problem. All right? So this is the end of the lecture. Thanks for watching.